Welcome to this coding walkthrough. Today, we'll be tackling problem number 2157, titled Groups of Strings. This problem challenges us to think critically about string relationships and how we can group them efficiently. Stick around as we dive into the problem and explore different approaches to solve it. In this problem, you are tasked with analyzing a list of strings to group them based on specific transformation rules. A transformation is defined as adding a single character, removing a single character, or replacing one character with another. Two strings are considered part of the same group if you can transform one into the other using one of these operations. The goal is to determine the total number of such groups and to identify the size of the largest group. For the input, you are provided with a list of strings, where each string consists only of lowercase English letters. The output is a list of two values, the total number of groups and the size of the largest group. For example, given the input words equals a, b, abc, the output would be 2, 3, indicating that there are two groups in total, and the largest group contains three strings. In the first example, the strings a, and abc form one group. This is because it can transform into a by adding the character b, and ib can then transform into abc by adding the character c. On the other hand, the string b is isolated because it cannot transform into any of the other strings using the allowed operations. As a result, there are two groups in total, and the largest group, which includes a, and abc, has a size of 3. In another example, where the input is words equals bc, cd, d, each string forms its own separate group. This is because no string can transform into another through the allowed operations. Therefore, there are 4 groups, and each group has a size of 1, making the largest group size also 1. Now let's consider the third example, where the input is words equals a, AAA, AAA. In this case, all the strings belong to a single group. The transformations occur as follows: A transforms into AA by adding one character, AA transforms into AAA in the same way, and AAA transforms into AAA. Since all the strings are connected through these transformations, there is only one group, and its size is 4. Additionally, note that there are constraints to this problem. The number of strings in the input list can be as large as 20,000, and the length of each string is at most 26. Every string is composed of lowercase English letters, making it essential to consider efficiency when designing the solution. The transformations allowed between strings are clearly defined. You can add one character, remove one character, or replace one character with another. These operations are bidirectional, meaning if string A can transform into string B, then string B can also transform into string A. To solve this problem, you can think of the strings as nodes in an undirected graph. An edge exists between two nodes if one string can transform into the other using the allowed operations. The task then becomes finding all the connected components in this graph. Each connected component represents a group of strings, and the largest component determines the size of the largest group. This graph-based interpretation is key to addressing the problem efficiently given the constraints. To tackle this problem, we first considered a brute force approach. The intuition behind this method is to compare every possible pair of strings in the input list to check if one can be transformed into the other by adding, removing, or replacing a character. This means we would iterate through all possible transformations for each string pair to determine group membership. However, when analyzing the complexity, it becomes clear why this approach is not ideal. The time complexity is n squared asterisk m, where n represents the number of strings and m is the average length of a string. This arises from having to compare each string pair and perform m transformations for each comparison. While the space complexity is relatively modest at n, the approach quickly becomes infeasible for larger inputs, such as when n exceeds 1000. Furthermore, the brute force method does not utilize any inherent properties of strings to optimize group detection, making it computationally expensive and impractical for large datasets. This led us to explore a more efficient alternative. The optimized approach we chose is based on bit masking combined with graph components. Here, we represent each string as a 26-bit binary number, where each bit corresponds to a character from A to Z. For instance, the string ABC is represented as a bit mask with the bits 4, B, and C set to 1. Using this representation, string transformations like adding, removing, or replacing a character can be handled with simple bitwise operations. Adding a character involves setting an additional bit, removing a character clears an existing bit, and replacing involves clearing one bit while setting another. Once we have this bit mask representation, we can build a graph where each node corresponds to a unique string, and an edge exists between two nodes if one string can be transformed into the other via a single operation. To identify groups, we use graph traversal algorithms like DFS or union find to find connected components. The complexity of this approach is much more manageable. The time complexity is O, n*m plus n*26, where O, n*m, accounts for generating bit masks, and O, n*26, comes from trying all possible transformations for each string. Space complexity remains O, n, for storing the graph and union find data structures. This approach is efficient and scalable, leveraging bitwise operations in graph algorithms to handle much larger inputs effectively. Ultimately, we selected the bit masking and graph components approach because it strikes the right balance between efficiency and scalability. The key insights that make this approach powerful are: first, representing each string as a bit mask allows for fast and compact transformation checks. Second, the string transformations themselves are reduced to simple bitwise operations, which are computationally inexpensive. Finally, detecting groups of connected strings becomes equivalent to finding connected components in the graph, a task that can be performed efficiently using algorithms like union find or DFS. This method avoids the inefficiencies of the brute force approach, which becomes prohibitively slow on larger datasets. While the bit masking solution does introduce additional complexity in terms of implementation, the performance gains it offers for large inputs far outweigh this drawback. The real breakthrough here is recognizing that string transformations can be mapped to bitwise operations, which drastically simplifies the problem and makes it feasible to handle thousands of strings efficiently. When evaluating trade-offs, the brute force approach stands out for its simplicity, as it is straightforward to implement. However, it fails to scale for larger inputs due to its high time complexity. On the other hand, the bit masking approach, while more complex to implement, is highly optimized for scalability. It makes effective use of bitwise operations in graph algorithms to reduce the computational burden significantly. Alternative methods for constructing the graph, such as using adjacency lists, were considered but ultimately proved less direct and efficient than bit masking for representing string transformations. By prioritizing scalability and performance, the bit masking approach emerges as the clear choice for solving this problem in scenarios involving large datasets. In this problem, we are tasked with determining the number of groups of strings where each string in a group can be transformed into another string in the same group using exactly one of three operations: adding a character, removing a character, or replacing a character. For example, the strings cat and bat form a group because you can replace the C in cat with B to get bat. Similarly, cat and cats are in the same group because you can add an S to cat. The first step in solving this problem is to define what we mean by a transformation relationship. Two strings are considered related if one can be turned into the other using one of these three operations exactly once. This relationship will serve as the foundation for grouping the strings efficiently. To solve the problem, we can start with a brute force approach. First, we take the list of strings as input. Then, for each string, we compare it to every other string to check if a transformation relationship exists. This involves using nested loops, where the outer loop iterates through each string, and the inner loop compares the current string with all others. For each pair of strings, we check the three types of transformations: adding a character, removing a character, and replacing a character. If any of these operations result in the two strings being equal, they are considered related. To group related strings, we use a union find data structure. Initially, each string starts as its own group. Whenever we find a pair of related strings, we merge their groups using the union operation. This process ensures that all strings connected through transformation relationships are grouped together. The key to solving this problem efficiently lies in the union find data structure and the way we check transformation relationships. Union find helps us group strings and identify connected components with two main operations: find, which determines the root of a group, and union, which merges two groups. To check if two strings are related, we compare their characters and determine if they differ by exactly one operation. This check can be performed in O, K, time, where K is the average length of the strings. However, the brute force approach of comparing every pair results in a time complexity of O, n squared asterisk k, where n is the number of strings. To manage this, we use union find with optimizations like path compression, which speeds up the find operation, and union by rank, which balances the merging of groups. Additionally, we store parent pointers and ranks in a hash table or array to ensure efficient access during these operations. To illustrate the algorithm, let's consider the example input, cat, bat, cats, cut. First, cat and bat are compared and found to be related because you can replace C with B. Their groups are merged. Next, cat and cats are related because adding S to cat gives cats, so their groups are merged. Then, cat and cut are related because replacing a with U transforms cat into cut, so their groups are merged. For the remaining comparisons, bat and cats, bat and cut, and cats and cut are not related, so no further merges occur. After processing all pairs, the union find structure shows that all strings belong to a single group. The output is therefore one group. To optimize this process, we can skip redundant comparisons using symmetry and pre-process strings by length, as strings with significantly different lengths cannot be related. These techniques reduce unnecessary checks and improve efficiency. To solve this problem, we start by importing the necessary modules, defaultIct for handling our graph and deque for breadth-first search. Then, we define our main function, groupStrings, which will take a list of words as input. Inside this function, we define a helper method called get_bitmask. This method computes a bitmask for each word, where each bit in the mask represents whether a specific letter from A to Z appears in the word. We calculate the bitmask by iterating through the characters of the word, and for each character, we set the corresponding bit in the mask using a bitwise OR operation. The result is a unique integer representation of the letters in the word. Next, we define another helper function add_edge to add edges between two bitmasks. This function ensures that the graph is undirected by connecting both masks to each other. After defining these helpers, we initialize a graph as a defaultIct of lists and a bitmask_count dictionary to keep track of how many times each unique bitmask appears. Finally, we process each word in the input, calculate its bitmask using get_bitmask, and update the bitmask_count dictionary to reflect the frequency of that bitmask. Now, we iterate through the bitmasks in bitmask_count to construct the graph based on valid operations. For each bitmask, we first handle replace or delete operations. These operations alter the bitmask by flipping one bit at a time, which we achieve using the XOR operation with one I, where I represents each bit position. The resulting mask represents a neighbor, and we use add_edge to connect the original mask to its neighbor. Then, we handle the add operation, which ensures that we account for adding a new character to the bitmask. For this, we check if a specific bit is not already set in the mask. If it isn't, we use the OR operation to add the bit and then connect the original mask to the new neighbor using add_edge. After constructing the graph, we move to the second step, which involves counting connected components and determining the sizes of these groups using BFS. We initialize a visited set to keep track of visited nodes, a number_groups counter to count the number of connected components, and a largest_group variable to track the size of the largest group. As we iterate through the bitmasks in bitmask_count, if a mask hasn't been visited, we increment the group counter, initialize a queue with the current mask, and set group_size to 0. This prepares us to explore the connected component containing the current mask. Within the BFS loop, we process each node in the queue. For the current node, we first mark it as visited and increase the group_size by the frequency of the bitmask from the bitmask_count dictionary. This ensures that we account for all occurrences of the current bitmask within the word list. Next, we iterate through the neighbors of the current node in the graph. For each neighbor that hasn't been visited, we add it to the queue for further exploration. Once the BFS completes for the current connected component, we compare the group_size to largest_group and update the latter if the current group is larger. After processing all the masks and their connected components, we return an array containing number_groups, the total number of connected components, and largest_group, the size of the largest group. This concludes the implementation, effectively grouping the strings based on their connectivity in the graph. Here, we start by importing the necessary utilities and defining our class and main method for the solution. The goal is to group strings based on their bitmask representations. First, we create a map called bitmaskCount to store the frequency of each unique bitmask. The getBitmask method, which we'll define later, converts each word into its corresponding bitmask representation by treating the characters as binary positions. For each word, we calculate its bitmask and update its count in the map. Next, we build a graph where nodes represent these bitmasks and edges represent connections based on single-bit differences. To do this, we iterate through all bitmask keys in bitmaskCount. For each bitmask, we create edges by toggling a single bit or adding a bit if it's not already set. These edges are added to the graph, ensuring connections between bitmasks that differ by one character addition, removal, or substitution. Now that the graph has been constructed, we proceed to find connected components in the graph using BFS. We initialize a set called visited to track the bitmasks we have already processed. We also set up two variables, number groups to count the number of connected components, and largest group to keep track of the size of the largest group. We iterate over each bitmask in bitmaskCount. If a bitmask hasn't been visited yet, it means we've found a new group. We increment the number groups counter and initialize the group size to 0. We then perform a BFS using a queue, starting with the current bitmask. During the BFS, we pull a bitmask from the queue, check if it's already visited, and if not, we mark it as visited and add its count from bitmaskCount to the group size. We also add all its neighbors in the graph to the queue, provided they haven't been visited yet. This ensures we traverse all connected bitmasks for the current group. As the BFS continues, we calculate the size of the current group by summing up the counts of all visited bitmasks within that component. Once the BFS for a group is complete, we compare its size with largest group and update the variable if the current group is larger. After processing all bitmasks, we return an array containing the total number of groups and the size of the largest group. Finally, we define the helper method getBitmask, which is responsible for converting a word into its bitmask representation. For each character in the word, we calculate its position in the alphabet using CEA, and then set the corresponding bit in the bitmask using the bitwise OR operation. This method ensures that each word is uniquely represented as a combination of bits based on its characters. With this approach, we efficiently handle the grouping of strings based on their connectivity in the graph. To solve the problem, we start by converting each word into a bitmask that represents its unique set of characters. For example, the word A is represented as the bitmask 1, which in binary is just a single 1 at the least significant bit. Similarly, B becomes 2, which in binary is 10, and A becomes 3, which is 11 in binary. These bitmasks are stored in a dictionary along with their counts. Next, we build a graph where each bitmask is a node, and edges are added based on character manipulations like adding, removing, or replacing a single character. For example, the bitmask for A, which is 1, has neighbors such as 0, 3, and 5, representing possible transformations. Similarly, AB with a bitmask of 3 has neighbors like 1, 2, and 7. This graph captures all possible connections between words based on these transformations. To determine the groups of connected words, we perform a breadth-first search, or BFS, on the graph. Starting with the bitmask 1, which represents A, the BFS explores its neighbors, visiting nodes 1, 3, and 2. This forms one connected component with a size of 3. Then, starting at the bitmask 4, which represents C, the BFS visits only node 4, forming a separate group of size 1. This results in 2 groups in total, with the largest group containing 3 words. Moving to the next example, we calculate the bitmasks for the words ABC, BCD, and ACE. The word ABC becomes 7, which is 111 in binary, BCD becomes 14, or 1110, and ACE becomes 21, or 10,101. These bitmasks are also stored in a dictionary along with their counts. With the bitmasks for ABC, BCD, and ACE, we now build the graph. For instance, the bitmask 7, representing ABC, has neighbors like 6, 15, and 23, corresponding to possible character transformations. Similarly, the bitmask 14 for BCD connects to neighbors such as 15 and 12, and the bitmask 21 for ACE has neighbors like 20 and 23. The graph is constructed to capture these relationships. When we perform the BFS, we find that each bitmask forms its own isolated group. Starting with 7, we visit only that node, forming a group of size 1. The same happens for bitmasks 14 and 21. This results in 3 separate groups, each containing just one word, with the largest group size being 1. Now, for the input consisting of a, ABC, BCD, and a, we calculate their respective bitmasks. The word is represented as 1, ABC is 7, BCD is 14, and AB is 3. These bitmasks are stored with their counts to help keep track of occurrences. Next, we construct the graph based on these bitmasks. For example, the bitmask 1, corresponding to a, has neighbors like 3. For ABC, which is 7, neighbors include 3, 15, and 23, while for BCD, which is 14, neighbors include 15 and 12. Finally, the bitmask 3 for AB connects to neighbors like 1 and 7. This graph makes it possible to identify connected components based on the relationships between these bitmasks. Using the constructed graph, we perform a BFS to count the groups. Starting with the bitmask 1, which represents a, the BFS visits nodes 1, 3, and 7, forming a connected component of size 3. Then, starting at the bitmask 14, which represents BCD, the BFS visits only node 14, forming a separate group of size 1. In total, we find 2 groups, with the largest group containing 3 words. This completes the breakdown of the examples, demonstrating how we calculate bitmasks, build the graph, and use BFS to determine the number and size of connected groups. Here, we are analyzing the time complexity of the solution by breaking it into 3 main parts. First, we calculate bitmasks for all the given words. For each word, we iterate through its characters to compute the bitmask based on their ASCII values, which takes m time for a single word, where m is the average word length. Since there are n words, this step takes n*m overall. Next, we construct the graph. For each unique bitmask, we generate its neighbors by iterating over all 26 letters in the alphabet, considering both addition and removal of a letter. This operation is linear in the number of unique bitmasks, denoted as k, resulting in k time. Finally, we perform a breadth-first search, BFS, to calculate connected components in the graph. In the worst case, BFS will traverse all nodes and edges, where the number of edges is proportional to the number of nodes, giving us k for this step as well. When we sum up these parts, the total time complexity is derived. By combining the complexities from the previous breakdown, we get n*m for bitmask computation, k for graph construction, and k for the BFS traversal. Adding these together, the overall time complexity is n*m plus k. Here, n is the number of words, m is the average length of a word, and k is the number of unique bitmasks. This shows that the algorithm scales linearly with respect to both the input size and the number of unique bitmasks. Now, we shift our focus to the space complexity. For the space complexity, we start with the storage for bitmask_count, which is a dictionary that holds the frequency of each unique bitmask. Since there are k unique bitmasks, this requires k space. Next, the graph is stored as an adjacency list, where each node can have at most 26 neighbors. The total space required for all edges is proportional to k, so the graph storage also requires k space. Additionally, the BFS traversal uses a queue and a visited set, both of which store at most k nodes in the worst case, adding another k space. When we sum these components, the overall space complexity is k, making the solution efficient in terms of memory usage. To better understand the efficiency of this approach, we compare it to a brute force solution. A naive method would involve comparing every pair of words to determine connectivity, which would result in a time complexity of n²*m. This is because there are n words, and each comparison takes m time for the average word length. In contrast, the graph-based approach reduces this to n*m plus k, which is significantly more efficient. The proof of the big O complexity lies in the fact that each operation scales linearly with either the input size or the number of unique bitmasks. Additionally, constants like the alphabet size, which is fixed at 26, do not affect the asymptotic complexity. The memory usage also remains proportional to the number of unique bitmasks and their neighbors, ensuring that the solution handles large inputs efficiently. Now, let's break down the best, average, and worst-case scenarios for this approach. In the best case, all the words share the same bitmask, meaning the graph has only one node, and BFS becomes trivial. The time complexity here is O, n asterisk m, as the graph construction and traversal are minimal. In the average case, the performance depends on the number of unique bit masks and their connectivity, resulting in a time complexity of O, n asterisk m plus k. In the worst case, every word has a unique bit mask, and each bit mask has 26 neighbors. Even in this scenario, the time complexity remains O, n asterisk m plus k, but the constant factors are higher due to the increased graph size. Regardless of the case, this graph-based approach is consistently faster than the brute force solution, making it the optimal choice for this problem. When tackling this problem, there are a few common pitfalls to be aware of. One major mistake is ignoring edge cases. For example, you might miss scenarios like empty inputs, strings of different lengths, or duplicate strings. These edge cases can lead to unexpected errors or incorrect outputs, so it's crucial to test your solution comprehensively. Another issue is relying on inefficient comparisons. If you use nested loops to compare every pair of strings, you risk an O, n superscript 2, or worse time complexity, which can be a deal breaker for large input sizes in competitive programming. Misinterpreting the problem is another frequent error. This happens when you assume constraints or conditions that aren't actually part of the problem, leading to overly complex solutions that are harder to debug. Finally, be mindful of your choice of data structures. Using something suboptimal, like lists when sets or dictionaries would be more appropriate, can slow down your solution and make it harder to implement efficiently. Each of these mistakes can be avoided with careful planning and testing. Now, another overlooked strategy is leveraging sorting where applicable. Sorting strings or data can simplify your logic significantly, especially for grouping or transformation problems, yet it's often missed. For instance, sorting might reduce the complexity of certain checks and make your implementation cleaner. In interviews, it's also important to focus on problem-specific patterns. Identify if the problem involves transformations, permutations, or equivalence classes, such as anagrams or rotations. Recognizing these patterns can lead you to specific optimizations, like using hashing. Always aim for optimal spacetime trade-offs. Interviewers generally prefer solutions with O, n asterisk log, n, or O, n, time complexities over brute force approaches. Data structures like hash maps and sets can be particularly useful for efficient lookups. Remember to communicate your thought process clearly during interviews. Explain how you're addressing edge cases and constraints, as this demonstrates structured problem solving. Lastly, validate your code thoroughly. Testing with edge cases and large inputs ensures robustness and helps you spot any overlooked issues. Looking at related problems can deepen your understanding and prepare you for variations. For example, LeetCode problem 49, Group Anagrams, challenges you to group strings that are anagrams of each other. Similarly, problem 438, Find all anagrams in a string, asks you to detect substrings that are permutations of a given string. Then there's problem 846, Hand of Straights, which involves grouping integers into consecutive sequences. Finally, problem 128, Longest Consecutive Sequence, focuses on finding the longest sequence of consecutive numbers in an array. These problems share conceptual similarities with grouping or transformation tasks, so studying them can help you recognize patterns and apply the right algorithms effectively. For alternative approaches, there are several strategies to consider, each with its own trade-offs. A sorting-based grouping approach, where you sort each string and use it as a key in a hash map, is particularly efficient for problems like anagrams. However, sorting adds an O, k asterisk log, k, overhead per string, where k is the average string length. Alternatively, you can use hashing with frequency counts, where character counts act as keys in a hash map. This avoids sorting but requires additional O, k, space per string. For problems involving equivalence or transformations, Union Find is another powerful tool. It helps you group items into connected components but can be more complex to implement. Lastly, dynamic programming is useful for optimizing repeated computations in transformation or sequence problems. While it can save time, it often requires additional space and can be harder to debug. Each of these methods has its strengths and weaknesses, so choose the approach that best fits the problem's constraints and requirements. Great job sticking with it. To wrap up, we reviewed the key takeaways and summarized the main points of the groups of strings problem. Remember to keep practicing and applying these techniques to other problems. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!